In this video, we're going to learn how to identify and model exponential growth and decay. So in order to do this, we're going to reiterate our point from the last lesson. Whenever that b value is greater than 1, this is known as exponential growth, and that b is the growth factor. Now, you can also represent growth with a rate. So if you ever say it's increasing by a certain percentage over time, that's known as a growth rate, and you would write b as 1 plus that rate. Now, if the b is between 0 and 1, that's a decay factor, and you have the percentage decreased, usually written as a negative decimal. That's called your rate of decay. So when I do 1 plus r, it's actually 1 minus the rate, which puts that b between 0 and 1. That would be your rate of decay. Your y-intercept is always going to be the a value in front. And we'll get into what this equation is when we get to the second part of this lesson. So without graphing, let's determine whether the function represents exponential growth or decay, and then we find the y-intercept. This can usually help you envision what a graph looks like without plotting any points initially. So right here, I'm looking at 12 times 0.95 to the x. I'm looking at the 0.95 since 0.95 is between 0 and 1. The function represents exponential decay. So since that's less than 1, it means that this function is going to decay over time. It means it's going to go downwards and flatten out to the right. Now, if that number there helps you determine if it's decay, the number in front should end up being your y-intercept. So it means that it'll intersect your y-axis at 0, 12. The reason why it's going to be 12 is if you plug in 0 for x, the 0.95 to the 0 becomes 1. So your y-intercept is 12 times 1, making it 12. So imagine a graph that you go to 12 on your y-axis, and then it flattens out to the right over time. And that's what the graph of this function looks like. Next up, let's look at y is equal to 0.25 times 2 to the x. Now, this 2 will be known as a growth factor because it's greater than 1. So since 2 is greater than 1, the function represents exponential growth. So we know that to the right, it's going to go upwards. It's going to grow to the right, and the value it's going to start at is whatever our y-intercept is. In this case, our y-intercept will be the number in front of that 2, which is 0.25. So our y-intercept is 0, 0.25. So it starts at 0.25, and then it grows to the right from there. Let me rewrite this answer so it could be a little more clear. So 0.25. Now let's talk about writing an exponential function. If you can get a rate of growth or decay, then we can use this little function. I know it's a little cluttered, but I just wanted to break it up. This a value is usually like the y value of these equations. It's usually the amount that you have after a certain period of time. The a that's in front of the parentheses of 1 plus r is usually whatever initial amount you have, kind of corresponding to the 12 and the 0.25 we saw earlier. Then on the inside of the function, instead of using b, you'll use 1 plus r instead, with r being whatever the rate is of either growing or decaying. And we raise to the t power, which is typically the number of time periods that you're dealing with. So putting this into action, for this function, I'll have a of t will equal, you've invested $1,000 in a savings account. So the amount pays 5% annual interest, and how much money will be in the account after 6 years. So the $1,000, what you put in, that's your initial amount. So we'll put 1,000, then open our parentheses, and do 1 plus our rate, which is 5%. It pays that, so it means we're going up, it means we're growing. So this is definitely a growth rate. So we'll do plus 0.05 for 5% raised to the t power. So my function is a of t is equal to 1,000 times 1.05 to the t power. So you can see here my y-intercept would be 1,000, and I should grow to the right because 1.5 is bigger than 1. Now, if I want to figure out how much money is in my account after 6 years, all I need to do is plug in 6 for t, and it will tell me. Now, we'll use a calculator to calculate this to save a little time, because that would be very tough to do in your head or by hand. We have 1,000 times 1.05 to the 6th power. So after 6 years, if my account was paying 5% in interest, I would end up with $1,340 and 10 cents if rounded to the nearest cents. Now let's write a model for the next situation. Let's say a population of 1,860,000 decreases by 1.5% each year for 12 years. So we should be decaying. So this will be a rate of decay. So we wouldn't use a positive value for this rate. But when I write the function, I'll have a of t is equal to your initial amount, which is 1,860,000, times 1 minus our rate of decay, because you do plus a negative, because I'm decreasing. That's 0.015 for 1.5% to the t. So a of t is equal to 1,860,000 times 9.985, whenever you do 1 minus 0.015. Oop, not 9 point, 0.985. Started with 10 instead of 1 there. But 0.985. You can see here that's less than 1, which means it represents decay. That makes sense since I'm decreasing over time. But now let's see what the population will be after 12 years. So a of 12 will equal 1,860,000 times 0.985 to the 12th power, which I'm going to use a calculator to help me calculate. So 1,860,000 times 0.985 to the 12th power, and the population ends up being 1,551,000, and then 400. And I'm going to round up because we don't want any fraction of a person. 486. Or round down, but make sure you round to a whole number to make sure you don't have any fractions of people living there. So one last note I want to point out is the only way any of these functions can be exponential is if it changes by a fixed percentage each time period. So if the percentage would change or alter over the 6 years, that wouldn't represent an exponential function anymore. So we have to assume it's an exponential function and that it stays 5% and then goes down by 1.5% every year for all those years. And that is how you identify and model exponential growth and decay.